Today we are going to talk about the Kramers degeneracy. So in EPR spectroscopy, this Kramers degeneracy is very important. Generally, when we have a methyl radical, so here we have a one electron. So this can be arranged either upward direction or downward direction. So it can be either plus 1 by 2 or minus 1 by 2, I mean spin. Okay, so in the absence of magnetic field, this will exist like this, plus or minus 1 by 2. So when we apply the magnetic field, so these energy levels will splits. Okay, so this will be lower energy, that is minus 1 by 2, and this will be higher energy, that is plus 1 by 2. Okay, this is in the presence of magnetic field. So this is called, the splitting is taking place only in the presence of magnetic field. So now if splitting takes place in the absence of magnetic field also, that is called as Kramers degeneracy. This is also called a zero field splitting. Why we are calling it as a zero field splitting? Because this is all this process is taking place in the absence of magnetic field. Okay, so but here it's in the presence of magnetic field, the splitting is taking place. Even though magnetic field is absent, in case of Kramers degeneracy, the splitting will takes place. Okay, and this Kramers degeneracy we can see for the metals which are having more than one electron. For D1 systems, we cannot see the Kramers degeneracy. The condition for the Kramers degeneracy is there should be more than one electron, greater than one electron. It can be D2, D3, D4, D5, so on. So then only we can see the Kramers degeneracy. So now we'll go for the D2 system. So in the D2 system, we have two electrons. These two electrons can be arranged in the three ways. When these two arrange in the upward direction, and this is one possibility, another possibility will be in opposite direction both, another possibility will be both will be in the downward direction. Okay, when they are present both in upward direction, that time spin will be plus 1, and here spin will be minus 1, and for this spin will be 0. And in the EPR spectra, in the absence of magnetic field, we have, see here this is in the absence of magnetic field. In the absence of magnetic field itself, we have two energy levels. So these two will consider as one energy level, that is plus or minus 1, and this will be another energy level, second energy level. Okay, so they will exist like this. This is 0 and this is plus or minus 1. So this is in the absence of magnetic field. So in the absence of magnetic field itself, there is a two energy states for D2 system. So when we apply the magnetic field, then again it undergoes splitting. This will be minus 1, this will be 0, and this will be plus 1. In the absence of magnetic field itself, there is a two different energy states, means splitting already takes place. Okay, and when we further apply magnetic field, again this plus or minus 1 further splits into two energy states. And here in EPR spectroscopy, we have two selection rules. Delta Mi is equals to 0 and delta Ms is equals to plus or minus 1, or plus or minus 3, plus or minus, like this. And this is for the nuclear transitions, and this is for the spin transitions. So in EPR spectroscopy, we don't discuss, in Kramers degeneracy, we don't discuss about the nuclear transitions. We discuss about the only spin. So the selection rule for Kramers degeneracy, either plus or minus 1, plus or minus 2, or plus or minus 3, or so on. And now there is a transition from here to here. This will be equals to minus 1, so this is allowed, and another transition will be from here to here. So this is also allowed because the difference between 0 and plus 1 will be plus 1. Okay, and if we consider this transition, this is forbidden because the delta ms is 0 here, so that is forbidden transition. For Kramers degeneracy, that delta ms should be plus or minus 1. So this is about the D2 system. And now we'll go for the D3 system. We have D3 system. So in the D3 system, there are 3 electrons. Those 3 electrons can arrange in 4 ways. All are in a upward direction, and here spin will be plus 3/2, and all will be in the downward direction. Here spin will be minus 3/2, and up, down, up. So this will get cancelled, then this will be plus 1/2, and next will be down, up, and down, and here this will get cancelled, then spin will be minus 1/2. So these are the 4 possibilities for D3 system. It can arrange in the 4 different ways. And now in the absence of magnetic field itself, it exists in the 2 forms, that is, this is plus or minus 1/2, and this is plus and minus 3/2. And for the, if we apply the magnetic field, it splits into two energy states. So this will be minus 3/2, this will be plus 3/2, minus 1/2, and this will be plus 1/2. And here we need to remember that always the least energy, the lower transition, lower this one spin should be minus value, because they should remember that ground state energy levels should be having a least energy. So because of that reason, minus 3/2 always comes down. If 5/2 is there, means minus 5/2 will comes always down. And here we apply the same selection rule, delta ms is equals to plus or minus 1. In that way, here we have one transition, and this second transition, and this will be third transitions. So here in the EPR spectroscopy, we will get a 3-line spectra for D3 system. Okay, and if they ask in the Kramers degeneracy for D3 system, how many lines you will get in the absence of magnetic field? How many lines in absence of magnetic field? For D3 system. So here this is in the presence of magnetic field, whereas this is in the absence of magnetic field, right? In the absence of magnetic field, we can see one line only, that is from here to here. Okay, if they ask in the presence of magnetic field, then to 3 lines. In the absence of magnetic field, we will see only one line. And same in the D2 system also, where we have D2 system like this, 0 plus or minus 1, and this further splits into like this. Okay, and in the absence of magnetic field, we see only one line. In the presence of magnetic field, we will see 2 lines for D2 system. And now we'll go for the D5 system. So here we have 5 electrons. If they arrange all in the upward direction, then spin will be 5/2, and if they all arrange downward direction, then spin will be minus 5/2. And other possibilities also there that we have to work out on it. So that is difficult to predict. We can, but it will take time. So I'm just directly writing the energy states: plus 3/2, minus 3/2, plus 1/2, and minus 1/2. So in this case, in the absence of magnetic field, we have a 3 energy levels. This will be plus or minus 5/2, this will be plus or minus 3/2, and this will be plus or minus 1/2. And now this is in the absence of magnetic field, a magnetic field absent here. And further, this will be split into two energy states. This is plus 5 by 2 and this is minus 5 by 2, and this also similarly minus 3 by 2 plus 3 by 2, and this will be minus 1 by 2 plus 1 by 2. And here we can see, in the absence of magnetic field, this is in the presence of magnetic field is present here, and here magnetic field is absent. In the presence of magnetic field, we can see 1 2 3 4 5 lines. We can see 5 EPR lines we can see. Okay, but in the absence of magnetic field, we can see two lines, from here to here 1, from here to here 1. So for d5 system, in the absence of magnetic field, we can see the 2 EPR lines, and in the presence of magnetic field, we can see the 5 EPR lines. And if you don't want to go for this procedure, like if in examination point of view, if they ask how many lines possible for a particular complex, like we have chromium plus 3 complex, they have asked. So they have asked how many lines possible for chromium plus 3 in a Kramers degeneracy in the presence of magnetic field. If this kind of question they have asked, you don't know anything about the Kramers degeneracy, and you don't know about the selection rule also. The simple trick is, in the Kramers degeneracy, number of lines equals to number of unpaired electrons. How many unpaired electrons are present in a complex, that many EPR lines we will get in a Kramers degeneracy. So we have a D2 system, the 2 unpaired electrons are there. So in the presence of magnetic field, we got 2 lines. And D3 system, we have already discussed, there are 3 unpaired electrons, so we got a 3-line spectra. And D5 system, there are 5 unpaired electrons, so we got 5 lines. So like this. So how many unpaired electrons are there, that many EPR lines we will get in a Kramers degeneracy. This is the blind indication. So just and chromium plus 3 means this is a D3 system. So without drawing all these things, we can simply say 3 lines. So this is about the Kramers degeneracy. And if they ask a question MnH2O 6 2 plus, so how many lines possible in the EPR spectroscopy for this complex? And this is the D5 system. So 5 unpaired electrons are there. 5 unpaired electrons means 5 EPR lines we will get. Okay, so this is about the Kramers degeneracy. And we can take another example, that nickel H2O 6 2 plus. So this is a D8 system, right? D8 system means how many unpaired electrons? 1 2 3 4 5 6 7 8. 2 unpaired electrons. That means we will get 2 lines in a Kramers degeneracy. So this is about the Kramers degeneracy. I hope you like my video. Thank you.